Okay, so to get started, first I want to thank the organizers and the reviewers for their work in selecting me and helping me review the conference paper we put together. This is a really different conference than a lot of the other conferences I go to, and it's exciting to be here and be able to contribute and talk about a tool that I put an awful lot of work into over the past year. And so before I even start, I'd like to recognize some of the other people who are on the team that helped me put this together. And so I am Tyler Martin. I'm a postdoc at NIST in the Material Science and Engineering Division. I've been a postdoc for about 2 years, and my postdoc advisors are Ron Jones and Chad Snyder, also in the Material Science Division. Ron Jones is the director of the Industrial NSOF Consortium, so as part of the development of this tool, we were heavily engaged with industrial participants, in particular Procter & Gamble, and so this is a tool we're not necessarily just developing for academia, we're developing this for everybody, including industry. And finally, we developed this tool in collaboration with my PhD advisor, Arthi J. Raman, at the University of Delaware, and in particular, one of our very talented graduate students, Thomas Gartner. And so, as my title indicates, today I'm going to be talking about my pyPRISM tool, which is a framework for conducting PRISM calculations. PRISM stands for Polymer Liquid State Theory, Polymer Reference Interaction Site Model, and it is a polymer liquid state theory. And so the first question you may be asking is, what is a liquid state theory? And so liquid state theories come in many forms, and I'm not going to harp on the details of what a liquid state theory is and what it isn't, but many of them deal with what are called spatial correlation functions. And so these spatial correlation functions, again, come in many flavors. And so, for example, we can consider this sort of coarse-grained representation of a polymer nanocomposite, shown in this diagram here, and we can consider this correlation function between the monomers in the polymer chains in the nanocomposite. So in the nanocomposite matrix, we have some spatial correlation function which is related to the probability of finding two monomers at a given distance. And so we have another type of correlation function called the direct correlation function, which I'm going to skip the details on. But as an illustrative example, we can also consider something called the intramolecular correlation function. And so this correlation function, rather than describing the correlation between different molecules, it's describing the correlations of monomers within the same molecule. And it is this separation of the intra and intermolecular correlations that is the foundation of PRISM theory and allows us to do the kind of calculations that I'm going to show you. And in particular, if you have any experience in small angle X-ray or neutron scattering, this is going to sound an awful lot like form factors and structure factors, and it should, because it's more or less the same thing. And we're going to talk about how we can use PRISM theory to predict X-ray and neutron scattering experiments. And so what exactly is PRISM theory? I've introduced these correlation functions, but what is the theory itself? And so before we get to PRISM theory, I like to do just a brief sort of historical walk. And so if we start a little over 100 years ago, we have Ornstein-Zernike theory, which describes the pair correlations in uniform isotropic atomic fluids, as shown by this diagram over here. And we can see that in Fourier space, we have a relatively simple algebraic expression which describes the relationship between our total correlation function, which again describes the correlations between monomers on different molecules, and the direct correlation function, which, without going into details, describes the correlations between molecules in the absence of many body effects. But overall, this formalism is limited to atomic fluids represented by spherical molecules that are isotropically ordered. And so Chandler and Loudon extended RISM theory in 1973, or extended OZ theory to RISM theory in 1973 so that they could handle what they call molecular fluids. So originally these were fluids like O2 and N2, and later they were able to extend it even further to small molecules such as acetonitrile. And the way they did this was by introducing a third type of correlation function, which now describes just the intramolecular correlations, and that's this omega function here. And you can see again, the formalism has gotten a little more complicated, but it's still algebraic, it's still relatively straightforward in Fourier space. So finally, Schweitzer and Kuro again extended RISM theory into what we now call PRISM theory, which allows us to apply the same mathematical formalism to high polymer systems. So now we can describe the correlations of molecules with many, in some cases, thousands of monomers, and predict the thermodynamic and structural properties of these systems, of these macromolecular systems. So what kind of things can we predict? So just as an overview, I've been talking a lot about pair correlation functions. We can also predict things like structure factors. So again, if you're a small angle X-ray or neutron scattering person, this should immediately excite you because we can predict exactly the things you measure in your experiment. We can predict thermodynamic properties such as the potentials of mean force between the various species in our system, second virial coefficients, chi parameters, binodal transition temperatures, equations of state, and so on. And so Prism theory isn't a theory which just gives you one piece of information. It's a theory which opens the door to a whole host of thermodynamic properties that you can rapidly calculate for your system. And I'm showing two examples in the bottom, which I won't go into the details of, but essentially we're predicting the structure factor of a polyelectrolyte system and the chi parameters of this nanocomposite, which has modified filler material as a polymer grafted nanoparticle. So, I've shown you the basics of Prism theory. I've shown you what we can calculate with Prism theory. Now, what kind of systems can we study with it? And so again, if we just do a brief overview, we can study systems like micelle solutions. And so here we're using Prism to model the small angle neutron scattering data of these worm-like micelle systems. And we can see that we're modeling the data quite well. And if you go back and you read this paper, you'd find that they don't have other ways or they don't have other good models to model this system. And so this is really the only way to extract meaning from this very expensive experiment. We can also we can do systems like nanocomposites or nanoparticle solutions. So here, rather than fitting the neutron scattering data, we're forward predicting the neutron scattering intensity of these silicon nanoparticles in solutions. So now we're not taking the data into account when we're constructing our model. We're just putting in a description into the Prism formalism and getting out a prediction for what we think the structure factor should look like. And so even though there are some deviations between the data, the experimentally measured data, and the Prism prediction, overall, I would say this fit is at least qualitatively quite good. So nanoparticle solutions are accessible. I already mentioned, complex nanocomposite systems. We can even do blank screens. Okay, let's do. Okay. Okay, we can do even systems which are sort of biological in nature, these polyelectrolyte systems. So here, they're modeling the structure factor of these tobacco mosaic virus particles. We can do copolymer systems of all kinds of different sequences. And so, Prism, again, is not just a theory for a small range of systems, it's a theory for an entire domain of systems. And even in going beyond that, okay, we're going to, one more time. Oh, okay, so going beyond that, Prism is quite flexible in its use cases. So a lot of the examples I showed you on the last several slides were simply for, forward predicting the properties of a system. And that's represented by this diagram at the top left. But we can also do things where we couple Prism theory to experiments or simulation in order to extend its applicability. So now we can gain the power of the rich metrologies that we've developed and feed them into Prism theory in order to make more accurate and better predictions for these systems. Prism can also be coupled with simulations in a self-consistent formalism, which can allow us to study highly non-ideal behavior in various polymer systems. One of the use cases of Prism that I'm most excited about is as an IQ model for scattering data. And so in the world of X-ray, small angle X-ray neutron scattering, one of the biggest challenges is understanding the data that we measure. And with Prism theory, we can take all of these models which we already have, which work really well in the dilute limit of systems, and use Prism to introduce intermolecular interactions and greatly extend their applicability. And so Prism takes theory that we already have and makes it better. And finally, recently, Prism has been developed into a coarse-graining engine, which allows us to take detailed atomistic models from simulation and sort of rapidly construct liquid state theory-based coarse-grain models, which can allow you to do simulations over much longer length and time scales. And so, to summarize everything I've said, in this first half of my talk, I would say Prism Theory can calculate many thermodynamic properties. It can characterize the material structure of many liquid-like polymer materials, is applicable to a wide range of polymer systems in the liquid-like space, and integrates well with experiments, simulations, and theory. And if you've never heard of Prism, that's probably not your fault, because Prism is, woefully underused across the community. And, the question I want to ask and answer is why. And so, we can put up some explanations, but I would say in particular would be the fact that there's no open source tool. There's no accessible way to get into Prism Theory. So if you decide tomorrow that you think Prism Theory would be really good for you, in the absence of the tool, which I'm about to talk about, you would have to spend a significant amount of time learning the theory just to decide whether or not it would actually be useful for you. We're hoping to greatly reduce the barrier to that so that you can at least explore the tool without having to take the sort of penalty of digging through the extraordinarily dense and technical literature that is liquid state theory. And so this tool is called pyPRISM, and it's a computational tool for Prism theory. And as I said, the main goal is to lower the barrier to accessing this powerful theory. And so, as I showed, this isn't a tool which is, just predicting one thing for one system. It has the potential, and it is broadly applicable. And so we want to give people the opportunity to ask themselves and to answer for themselves, can this enhance my research? Can this, help me get to better answers more quickly? And so, I've already put up the GitHub. So pyPRISM is up on GitHub in the US NIST organization. It's up on Read the Docs under pyprism.readthedocs.io. There's an interactive tutorial, which we're going to be going through in just a second. So you all will be able to follow along if you want and try out pyPRISM for yourself via a binder instance, which I have set up. We have a review article, which goes through the details, more of the theoretical details of Prism theory as a formalism. But the SciPy proceedings we wrote to accompany this talk go into great detail, or go into much more detail on the code side of things. So depending on your interest, we have 2 papers out on pyPRISM that have a whole lot of information both about the theory and the tool itself. And so one of the things that I want to highlight is one of our focuses with pyPRISM is very much on pedagogy. And so we recognize that in developing a scientific tool, we have additional challenges which don't necessarily exist for every computational tool that's developed. Because on top of teaching people our API, we also have to ask ourselves whether or not they know the theory that they're going to be used, and whether or not they need to know the theory that the tool uses. And so we've really tried to put a lot of effort into not only giving people access to materials that teach them pyPRISM, but also guiding them towards the right way to apply and use the theory. So towards that end, we've developed a series of Jupyter notebooks, which again we hope to grow and to continue to change, but we've developed a series of Jupyter notebooks which teach people these different features which I just outlined. And so, we discuss things, we start out very general with explaining how do you use a Jupyter notebook, and what is Python, and what is NumPy. We move on to the details of Prism theory and how to use pyPRISM. We have several notebooks which focus on case studies. So if you know a little bit about Prism theory but don't know how to use it for a nanocomposite, we have 2 very detailed case studies which I'm going to demo for you in just a minute, which can show you how to use it for a nanocomposite system. And we intend to grow this. We intend to add more case studies and more systems so that everyone should have a starting point, a detailed, explanatory starting point for the kinds of systems they're interested in. And finally, for our advanced users, it's the goal, I think, of every open source project to have people contribute back. And we have a couple of notebooks which go through the details of the guts of pyPRISM, and how, we put together the class structure and the choices we made, and also how to do some more advanced things with Prism theory. And so I'm going to jump out of this presentation and move to a web browser. And so if you navigate to github.com/usnisgov/pyPRISM and you scroll down, there's a binder button which will launch you into these very notebooks that I'm about to talk about. You can also go to the documentation, and if you go to the tutorial page and you scroll down, there's a binder button here as well. And so these will both allow you to follow along with the next several over the notebooks I'm about to talk about. So how much time do I have left? 7 minutes. 7 minutes. Okay, so plenty of time. Okay, so, right off in the notebook, right off in these tutorials, we wanted to make sure the users get a sense of whether or not they were moving in a direction that was going to be useful for them. And so here, in the very first notebook, so this is NB0.introduction. We immediately discuss, what kind of systems can be studied with pyPRISM, because if you're doing something if you're studying a system that's not applicable to the tool, we don't necessarily want to waste your time with learning the details of pyPRISM. So we tell you, what can you study with pyPRISM? What kind of things can you calculate? What are the benefits of using Prism Theory over another molecular simulation or theory method? And these are things I didn't talk about, but Prism Theory, as I'm about to demonstrate, can be solved in seconds. This isn't something where it's going to take days or weeks of sampling to get an answer. We can literally get an answer in about between 1 and 30 seconds generally. We don't have finite size effects like a simulation method does. We don't have to worry about equilibration. If we get an answer, it is equilibrated. And we're mostly free of incompressibility assumptions, unlike a lot of SCFT methods that you might apply. But an important question is where can't you use pyPRISM? And so pyPRISM is not applicable in its base form for macrophase separated systems, for non-isotropic phases, systems with strong directional ordering, or if you're interested in dynamical properties. It's an equilibrium theory. It predicts equilibrium static properties. Okay, and so to move on to the tool itself, so in the fourth notebook, we're going to skip three of the notebooks in between, but in the fourth notebook and before, we actually introduce pyPRISM and how to use it. And so, we start off the notebook with we assume no base level of knowledge with Python or with any of the Python tools, and so we explain to the users immediately. I think one of the first things we realized with a lot of the people we tested with is that this import cell can cause a lot of problems. If sometimes the import errors you get here are completely foreign to people who don't do programming and who aren't Python programmers. And so, assuming that your environment is working, we move on. We instantiate a system. We say, this system's going to be at a thermal energy level of 1.0. We're only going to consider one component. And so for this first example, we're going to be considering the classic Lennard-Jones fluid, which is not a polymer system, but is still accessible with pyPRISM. So we create a system. We define our solution domain. So pyPRISM is essentially a set of equations that we're solving. And so we need to define the discrete domain that we're going to solve the equations over. And so we define a grid spacing and a grid length. So we're going to solve with a real spacing of 0.005 and a length of 32,768. And we can see that this automatically creates our real space and our Fourier space solution grids that we're going to solve over. We're going to define the interactions of our system. And so I said a Lennard-Jones system, but instead we're just going to do a hard sphere solution. And so we set the monomer potential to be hard sphere, and we set the monomer diameter to be 1.0. We define the system density, the site density of these monomers, and we see that that's set to 0.8. We define the molecular structure through the omega, and I'm kind of going fast through this. The point is just to sort of demonstrate the tool. These notebooks are online. You can go back through and read them in more detail if this is of use to you. We define closures approximation, and finally, we solve the system. And so this is one of the things I wanted to highlight, because even for a relatively simple case like this, if you were to take and you said, I want to do a molecular dynamics simulation of a Lennard-Jones fluid, that's a trivial task. But it still takes a finite amount of time. Even on modern resources, this is probably going to take you, for a reasonably sized system, minutes to hours to maybe a couple hours, depending on how big you're going. And I just solved the Prism equations on my laptop in about a second. And I can get predictions that I don't have to worry about sampling, I don't have to worry about finite size effects. And as you'll see, my curves are very smooth, they're not histogrammed. And so to show you, we can plot the results from that calculation. And so this is the pair correlation function for this hard sphere fluid that we calculated in about 2 seconds with pyPRISM. We built these notebooks using bokeh and hollow views, so users can go in and play with the plots and zoom in and explore the data. Another benefit of pyPRISM is that once you've done the calculation, the solved correlation functions are stored in memory or are stored in a memory object so that you can do multiple calculations in a row without having to redo the calculation. So we just calculated this pair correlation function. We can say, okay, pyPRISM, give me the structure factor now. And we can get the structure factor out without having to repeat that calculation. It's just a different way of mashing together those correlation functions. We can also calculate scalar data like second virial coefficients. So here I'm using pyPRISM to calculate the second virial coefficient for the system, and it's 0.6. This notebook is designed to walk users through in a step-by-step manner all the different pieces of the pyPRISM tool, but at the end of it, we want to give them sort of a sandbox to play with. And so if we scroll down, we can see that that entire calculation, if we take away all the explanation, is about 12 lines of code. And so in about 12 lines of code, we specify all the details we need to about this relatively simple system, and we're able to solve it, and we can overlay that solution. So here I'm overlaying the solution, a slightly different set of parameters over that the pair correlation function we solved for originally. And again, as you saw, this case took just a little bit longer, but we were still able to rapidly achieve a solution. And so I'm running out of time, but just to show you that pyPRISM is applicable to systems which are non-trivial, if we scroll down, one of the last studies I did during my PhD was to study this composite system. So this is a polymer grafted nanoparticle where our polymer grafts have this rather complex comb polymer architecture. And we were interested in how the properties of this comb polymer architecture affected the interactions of these nanoparticles. And so using pyPRISM, we can rapidly solve the properties of the system and calculate the potentials of mean force between these grafted nanoparticles for these different architectures. And I want to highlight this is a really non-trivial system. And one of the things we're showing here is that for the users, we overlay data that we've extracted from the literature with the prediction that comes from the notebook. So if the users start playing with parameters, or they start trying to write this code themselves, they can instantly get an idea whether or not they're doing the right thing, that they're making predictions which have been vetted and reviewed in the literature. And so just to wrap up, I want to say that, again, all of these notebooks are online, and if I go to my closing slide, I'll have all of that information there. Again, we have the review article, we have the SciPy proceedings. So I unfortunately have to run right after this talk because my flight is in about a couple hours. So I put my email up on the slide. If you have any questions, if you'd like to use pyPRISM, please contact me. We want users for this, we want suggestions, and we're pretty excited for the future of this tool. So thank you.
Any questions?
Real basic question. I'm new to polymer chemistry. What do you mean when you talk about correlations between molecules? Is it like intermolecular forces, or does that mean something else?
It's really spatial correlations. And so those correlation functions are related to the probability of finding those two sites at a given distance. And so, yeah. And you can imagine that you can have two monomers that are in the same molecule versus in different molecules, and so those are different probabilities, right? And so, but rather than tracking the probabilities directly, we're tracking the correlations, which is a ratio of those probabilities, if that makes any sense.
Yep.
Yeah.
Yep. Okay.
Hmm?
Thank you.
Any other questions?
Thank you, Tyler. One is a suggestion for us
Yeah.
that think in nanometers and stuff. It'd be nice if you, in the tutorial somewhere, you could build something that went from reduced units to real units.
So if we go to the documentation and we click API util, we have this unit converter package.
Oh, nice.
Which does exactly that. And so this
Okay.
allows you to define, you still have to define your reduced unit systems. You're going to have to define your energy scale, your length scale, but it'll automatically do your conversion back to the real units that you like.
Okay, great. This comes to my question. So where are you getting your potentials from? Is this you need to define up front?
Sorry, what was the last part?
Where are you getting your potentials?
Yeah. So right now we're using sort of just the classic potentials that everyone uses in the coarse-grained world. We have the Leonard-Jones potential, Wheat-Chandler-Anderson, Hart sphere, these sort of things. But there's no reason why you couldn't use a tabulated potential from any force field that you can imagine. And so As long as your potential can be expressed as a two-body pair function, then it could be used with pyPRISM.
So along those lines, what happens if you plug in a React or a Stillinger-Weber or something that doesn't obey the guidelines you said are for validity?
So it's more of a, I would have to think more about that, but my off-the-cuff answer would be it's more of an answer of how the mathematics work. And so at the end of the day, we have, vector representations of these potentials, and we sort of mash them together in the Prism formalism. And so if you can't give me a function of radial distance, I don't know, I would have to think really hard, and I'd have to know more about how that would be input into Prism. Because at the end of the day, I need a one-dimensional vector that represents the value of the potential on my solution grid. Otherwise, yeah. Because one of the things that's really different about pyPRISM than most molecular simulation methods is at no point in time do I have access to a coordinate trajectory. So I only have the correlation functions.
It's not my field at all. My sense is things like embedded atom potentials, many of which I think do give you that potential versus distance, but they clearly support crystalline materials and things like that. So I was just curious what happens in a paradigm of something that's so focused on liquid-like behavior.
It'd be interesting. If it can.
You're saying, Tyler, that all you have to do is put in your epsilon, your sigma, and this thing just goes.
Yeah.
Okay, it figures out the analytic potential for it. And stuff.
Yeah, so if you go to the potential subpackage, these are the potentials we have so far. So we have exponential, hardcore Leonard Jones, hard sphere Leonard
This
Jones.
just comes to your question. I mean,
Yeah,
if
yeah,
that's, if
yeah,
those functions, analytic functions got embedded, you cannot put many-body potential in
Yeah,
there.
so, yeah. I think-
So does your package also calculate the thermodynamic units like the energy and stuff like that?
So this is a good question. So depending on exactly how you define free energy, the potential amine force is a free energy curve. It's a free energy. It's the free energy of bringing two particles from an infinite distance to that distance in space. But in terms of a generalized free energy as a function of the number of particles or something like that, I don't think that's accessible with pyPRISM. But I can tell you that with the thermodynamic correlation functions, which you solve for, you can do an awful lot. So I can calculate things like, I can't remember, chemical potentials and things like that. So I have access to a pretty broad range of thermodynamic properties, but the raw free energy I think is difficult for me to access.
How about non-equilibrium systems or homogeneous systems?
So those are two separate cases, right? So for non-equilibrium, Prism Theory is an equilibrium formalism. So it's derived for the equilibrium grand canonical ensemble, and so it's not. It won't be applicable to anything that's non-equilibrium. But in terms of inhomogeneous systems, Prism in its base form is not, but Prism, as I demonstrated, can be coupled to other theories. And so what people have done is they'll do sort of a DFT or an SCFT calculation for a global system in order to get the phase separation, but then the structure of each of those individual phases can be calculated using Prism Theory.
Oh, okay. If they keep phase separated.
Yeah. And so
in different domains.
yeah, so Prism Theory can handle the individual domains, it just can't handle the interfaces and the interactions between the domains. But you can couple it to a theory that can.
Okay, and one more question. Have you heard about this integral equation coarse-graining theory? So
actually, I referenced that in my talk somewhat indirectly. So this is exactly integral equation coarse-graining.
Oh, it's included.
So we don't have features in Prism Theory, in pyPRISM, to do it yet, but there's no reason why we want to work towards it. So I didn't say this, but pyPRISM is about 2 months old in terms of it being released. I started writing it in August, and so it's very new. But I met a couple of the developers of IECG at a conference a few months ago. They were very interested. It's more of a bandwidth thing at this point. But
okay.
We are very interested in developing that angle for pyPRISM.
Okay, looking forward. Okay.
Thank you.
If there are no further questions, I'd like to thank this great collection of questions here. We are on break now until 3:30. I hope you'll all come back. We've got 3 more speakers this afternoon in this materials mini symposium track. I'd like to thank Tyler, and don't miss your plan.
Yeah, thank you.